Okay, now I'm working on lab 20, part 5.1. I'm going to measure the on resistance of the DG403 analog switch. So if this were a perfect switch, it would be like a 0 ohm resistor when it's on. But in fact, it has some small resistance, which I think is on the order of 20 ohms. So we put the scope here, we'll see with the voltage divider effect. If we put a few volts here, then if this were 0 ohms, we would see 0 volts here. But if this were a kilo ohm, of course, we would see 1.5 volts here, say, if this is a few volts. So we're going to see by what fraction of this signal we see here what the ratio of this on resistance is to the sum of these two resistances. And of course, this number will be much smaller than this number. So basically, this divided by this will be approximately the ratio of this signal to this signal. Okay, so meanwhile, I had to wire up. This is like page 8. I had to wire up the DG503, which is actually a pretty tricky thing to wire up. And we can go around the pins here. So I'm using the analog discovery board and I'm using my two 9-volt batteries to give me +9 and -9. And actually here, I will, I actually checked it with the scope. I won't check it again, but I put +9, +5, 0, -5. Okay, so 4 power bars, power rows. So up above I have +9 and +5. Down below I have 0 and -5. And I had to wire pins 11, 12, 13, 14 according to Tom's directions to be respectively +9, +5, ground, and -9. He writes +15 or -15. I'm saying +9, -9 because that's what we have with the batteries. I think this could be done entirely with +or -5. I haven't checked that yet, so I plan to check that next. Here's my signal source, the yellow wire. Here's scope probe channel 1, the orange wire. Here is a 1 kilo ohm resistor, and it's going into the S1 input of the DG403 chip. Meanwhile, I am probing the S1 input with channel 2 of the scope. And then pin 15 is the switch. So this is saying I want switch 1 to be closed. In other words, this MOSFET analog switch is in the on position. And then also you never leave CMOS inputs floating. You saw why earlier in this lab. You can get totally unpredictable results. So there's an unused input which is pin 10. So pin 10 is an unused CMOS input, so I grounded that. Okay, then I am looking at waveforms. So I have over here a 1 kilohertz sine wave, amplitude 3 volts. I guess that's fine. And 3 is not a round number, but we've got Mathematica to help us do math. And Mathematica, I'm going to open up Mathematica while I'm thinking of it. Okay, now let's go over to Mr. Scope. And you can see, so the yellow waveform is what we're sending into the this is upstream of that 1K resistor. And then this blue trace is channel 2 of the scope. So this would be exactly ground if the DG403 were a perfect switch with 0 resistance, but you can see that some fraction of that input signal shows up here. So these are on the same scale, no offset. Now I'm going to take channel 2 and change the scale. There's a factor of 10. Oh, that's pretty good actually. There's a factor of 20. There's a factor of 50. Okay, so actually, here, this is pretty good. I can just tweak this. Oh, that's pretty good, actually. A factor of 33, because that goes from 1 volt per division to 30 millivolts per division. See, so if I say, how do I get my mouse back? Okay. 1000, well, you know that you could do this in your head, divided by 30. So that's 1 volt divided by 30 millivolts, you get a factor of 33. So I think what that tells me, since the signal that I observe, here is 1/33 of the signal that I observe here. So that tells me that the on resistance of this divided by 1K is approximately 1/33. It's not exactly right because it's, well, here, we can do it exactly. We can say solve R on divided by R on plus 1000 ohms equals 1/33 roughly. And we get R on is about 31 ohms. Okay, fine. So we get an on resistance of roughly 30 ohms. That means that this analog switch, when it is in the on position, a perfect switch would have a 0 ohm resistance. This switch actually has something like a 31 ohm resistance when it's in the on mode. So I don't know, that was kind of cool. That was straightforward to do this way. I'm actually going to go and pause. I'll come back in part 2 of this little video and see if I can make it work without the 9-volt batteries, just for fun, using the plus and minus 5 of the analog discovery device. Oh, one other thing I was going to say is, so this is the DG403 analog switch, and you have to be careful when you insert this into the breadboard. For one thing, you want to do as you did when we were working with op amps, and you have to use this part of the breadboard. You have to be careful to find pin 1, which has the little dot, and make that the lower left. And then notice on this chip, notice that some of the legs are a little bit bent. So before you insert the chip into the breadboard, you want to check and make sure that you don't have bent legs. And if you do, try to find like a pair of needle nose pliers, or maybe you could use like a kitchen butter knife and straighten it out. Otherwise it'll snap off when you try to push it into the breadboard. And then when you take these chips out of the breadboard, try to pry them up gently from both sides at the same time, because the way the pins get bent like this is the chip is in the breadboard and then somebody pulls it up by one side only, and that bends the pins on the extreme end. So try to avoid that, because unlike most of the chips we use in this course, the DG403 is actually expensive. They're like $10 or $20 for a chip. Okay, so I'm going to come back in a moment and see what happens if I try not to use the 9-volt batteries, just use 5 volts plus or minus.